In this video, I want to talk about, well, what happens if I multiply or divide or change my function to a negative? How does that affect the graph? And how do we call, what's the proper terminology for those transformations? But before I do that, I wanted to also mention that if we have both adding and subtracting on the inside and outside, those transformations will both be applied together. So like looking at this example, x plus 1 inside squared minus 2 outside, we could look at those together and, both transformations will be applied. So the plus 1 on the inside, again, inside is always horizontal and it's in the opposite direction. So this would be a horizontal translation and this would be left 2 units because it's always opposite direction to the sign on the inside. And the minus 2, since it's on the outside, will be a vertical translation and it will be in the same direction as the sign. So this would be down 2 units. And sorry, that was horizontal left 1, not 2. I don't know why I put 2 there. I think I was getting ahead of myself. But basically both of these things will be applied. And so since the baseline function again was x squared in that case, which has a vertex at 0, 0, this is kind of another way of looking at it, but the vertex of x squared is at the origin. And what this is saying is I'm going to take that vertex and move it left 1 down 2. And that's again another reason why the vertex would be at negative 1, 2, as we discussed before. Sorry, negative 1, negative 2, because I'm going to take the origin, go left 1 down 2. And that's exactly why we have x minus h squared plus k, because the y coordinate of the vertex happens in the same sign as the outside number, whereas the x coordinate happens at the opposite sign for the exact same reason. And again, that same idea applies to any function. So this function would be shifted to the right 2 units and up 1 unit. And then again, that square root, we don't call it the vertex though technically, since it is a half parabola, it would be kind of like a vertex, but that would be that starting point for the little rainbow. And that's how you could imagine what this graph looks like without having to do anything. And again, that's the value of transformations in general. So next, the main one thing I want to talk about in this video is what about multiplying, what about dividing, how does that affect the shape? Which again, you might already kind of have a general idea, but let's just be very rigorous. So let's take the same approach we did before where let's just graph the baseline. So in each one of these, notice that the baseline is x squared. In this one, h of x, a negative has been applied. Here in k, 3 has been applied multiplicatively. And here we've multiplied by 1/2, which is the same as dividing by 2. So in all of these examples, I'm just examining what happens as we do other sorts of multiplication. So let's start with the baseline x squared, and we could also graph on top of it negative x squared. And when you hit graph, one of the nice features, notice that I don't want to put negative in parentheses because this is not in parentheses, and that would actually be different because the location of the negative matters whether it's inside or outside in the same exact way adding 3 matters whether it's on the inside or outside as well. And actually for multiplying, same deal, which we'll summarize at the end of this video. How do you know what all is going to happen? But when you hit graph in your calculator, actually I can make the view screen bigger, which is I probably should have been doing this in all my other videos, but I just kind of forgot, so it's easier to see. But as it's graphing, you'll see that it'll graph y1 first and then y1 second. So first graph, I can go ahead and hit graph. It will graph x squared, same as we already know what it looks like. And notice next it graphs negative x squared, which we can see is the same parabola. It's just completely upside down, which we often refer to as a reflection. So basically, in summary, what does a negative do? Well, and this also makes really common, it's very common sense to me, is that, well, it's going to take all those values and make them negative, right? So, I had the point 1, 1. Well, if I multiply by a negative, it's just going to be 1, negative 1. 2 normally makes 4. But if I have a negative, it's going to be negative 4. Because that negative is not being squared, it's on the outside. So what I would have is just negative 2 squared. 2 squared is 4. So what I'm going to end up with is just negative 4. And same, 3 normally produces 9 when I square it, but if I put a negative on the outside, I got negative 9. And so all of those values are the same, but they're upside down, which creates this reflective property. And it's sort of, we call it a reflection because it kind of looks like the shape of you when you look into the water or into a mirror. It's the same exact shape, but it's technically not because it's backwards. It's a mirror image, or a reflection of itself, which is why it's not just like the same thing. It's not been shifted down. It's actually upside down completely. So anyways, looking at the graph, if you're taking notes on paper, you could sketch all these things or whatever you want, but we would call this a vertical reflection. And actually, another way we phrase this, which is a little bit more proper, is we often say it's a reflection about the x-axis. Because notice each one of those points is upside down, but it's moved across the x-axis. All of them, it's like respect to the x-axis, because normally it's 1, now it's -1. And I can kind of imagine it's flipped across that. Or one way I like to think about it is a reflection is sort of like turning the page of a book. If I turn the page, the image will be backwards if I'm looking at it upside down. And same thing kind of here. I'm kind of like taking that image, flipping it down like this. And the axis to which I'm reflecting it is like where the axis is for the spine of the book, where the page is being turned about. That image is being turned about the x-axis. And so, or you could say it's a reflection about the x-axis. And, these are all different ways of saying the same thing, but this is the more proper mathematical way of saying it. And if you're wondering, well, how would I flip it about the y-axis? Well, that would actually be, instead of applying a negative on the outside, would be applying a negative on the inside. Which in the case of x squared, this would mean something entirely different. Actually, this would do nothing, because a negative squared would be negative. And in the case of this graph, notice that if I were to flip the image of the parabola about the y-axis, it would be the same exact shape, because it's actually symmetric about the y-axis already. And we're going to talk about that more later, because this is what we call an even function, and that's all coming up in a video soon. So looking at the last two, what about if I multiply by 3 or divide by 2? What does that do? So I'll go ahead and graph this on y3. Let me make this a bit bigger, and go ahead and graph 3x squared next. So looking at the shape, this would be this new curve in the middle right there. And so notice that it sort of looks like the same curve, but it's been sort of smushed. Or it's, another way to look at it is it's the same curve, but if we've stretched it out, that's exactly what's been what's happened here. And so, anyways, it kind of depends on the way you're looking at it. And every multiplier can be looked as either horizontal or vertical in the same way. But it all is it's kind of in the same idea as, well, what's happening to the outside versus what's happening in the inside. And since the 3 is on the outside, it's not in parentheses. One of the ways you would look at this is something's going to be happening vertically to this graph. And if I'm thinking about it on the vertical sense, it's sort of like taking that shape and imagining, well, what am I doing to it? It's like if I take that shape and I stretch it out vertically, it would create sort of like imagining a rubber band here. If this is our rubber band, if I stretch it in the vertical direction, it would extend and it would give us that same shape. So it's the same curve, it's just been stretched vertically. So anyways, the summary here is like one of the ways I could look at this is a vertical stretch. Or we could say it's been stretched vertically by a factor of 3. So that would be a more proper way to say it, by a factor of 3. And obviously a larger and larger number to which I'm multiplying by would have a more extreme impact. It would get narrower and narrower and narrower, or it would stretch it further and further and further. But technically, another way you could view it is, some of you might see this and it might not seem like it's been stretched. It might seem like it's been compressed or smushed inwards. And technically, a vertical stretch for this function is equivalent to a horizontal compression, which we often call shrinking, a shrink factor. And so this is something on a test that I'm not going to sweat the difference between these, because with some functions, it's kind of hard to tell the difference. And at the end of the day, it's not a big deal. But knowing that if you multiply by 3, it will stretch the curve out. And really, it's just because I'm taking every value of that function. If I multiply by 3, it's going to get larger and larger and larger, faster and faster and faster, kind of like on a line. And that is what causes it to stretch upwards faster and faster. And now if I multiply by a fraction, or again, you could think about that as dividing, it's going to do the exact opposite thing. Instead of stretching it vertically, it will shrink it vertically, and I will get a much fatter looking parabola instead. So let's just type it in 1/2 multiplied by x squared, which is equivalent to x squared over 2. And again, that would be my original x squared. X squared over 2 is going to be, instead of being stretched, it's going to be shrunk. So I can kind of imagine it looks like it's being smushed vertically, like imagine somebody sitting on it and it kind of getting that, I mean, you could say it's been stretched. Again, it's kind of the difference between opinion. It's being stretched horizontally, but it's being shrunk vertically because that curve is being kind of smushed downwards. Again, this was the original. This is the result of 1/2. It's small. It's sort of smaller. Again, there's a lot of ways you could describe it, but the correct mathematical way of saying it would be a vertical. It's been shrunk vertically. Vertical shrink or shrunk, depending on your tense. And again, that would be by a factor of 2. Or, you know, you might wonder, should I say it's been shrunk by a factor of 1/2? Or technically it's been stretched by a factor of 1/2. It's been shrunk by a factor of 2. Again, I don't really worry about all the technical terminology. It's not that important, but what is important is understanding what will happen when I'm multiplying by a number larger than 1. It will get stretched upwards. If I multiply by a number smaller than 1, it will get stretched or shrunk vertically, stretched horizontally. Anyways, that's enough on this one. Oh yeah, but also on the next page of the notes, we have sort of a summary. With stretching or shrinking, it's all about multiplying. So it says to graph y is equal to cf of x, meaning if I have a function where I have a multiplier, which we often call a coefficient, like 2x squared or 3x squared, it says to stretch the graph y f of x vertically by a factor of c, which is exactly what happened, right? When we had 3x squared, we said it was vertically stretched by a factor of 3. And it says if c is between 0 and 1, shrink it. So it would be a vertical shrink, as I was saying, instead. So if you're having a hard time figuring this out or parsing which is which, you can just follow the rules, which again are in the textbook in 2.2 or on the lecture notes, because it states exactly what's going to happen. But again, I wanted to focus on why and how can you kind of tell what will happen in these videos. And then if I'm multiplying on the inside instead, which I didn't actually look at this, it's exactly the opposite. Instead of stretching it vertically, it's going to stretch it horizontally with a large number. And it depends on the function, but it's for the exact same reason. When I multiply on the outside, it's just going to be a net multiplier to the entire function, which will just take the values and stretch them this way. When I multiply on the inside, it's going to stretch out the x input, so it's going to move it horizontally instead. And it's, you know, each one of those can create different shapes depending on the curve. And also when I have negatives, as I was discussing, when I have a negative on the outside, it's going to be a vertical reflection across the x-axis. So again, notice this is just another thing I wanted to sort of wrap up in this video. Outside is always, the transformations are always applied vertically. When it's on the inside, it's always applied horizontally, which would flip it across the y-axis instead. And again, like we often refer to it when it's flipped across the x-axis, it's upside down, which is why it's a vertical transformation, or reflection is the proper term for flipping it in that way. Anyways, this will wrap up our discussion on reflections, translations, stretches, and shrinks. But basically all of those fall into a category of different types of transformations. And let's say we applied every single one of these to something. Let's say we had negative 3x plus 4 squared minus 11. Again, this has, oh, you can't see what I'm writing. There we go. This has all of it, every type of transformation kind of put into one. And, you know, what's also kind of nice is if we know, like, well, this is just a parabola. Again, we have our vertex form like this. We can kind of tell all of those things just by, if we know what A, H, and K stand for. But, you know, if we know our transformations, those sort of ideas apply to all functions, you know, and we can apply a lot of the concepts that we've been learning for where's the vertex, what does A mean, and apply them to any type of mathematical function. Like, and again, in this particular case, this would mean a horizontal transformation to the left 4, a vertical transformation down 11. And this minus 3 would be, well, 3 means to stretch it vertically by a factor of 3, and negative means it will be upside down. So if I kind of put all of those, or, again, more formally, a vertical reflection. If I put all of those together, well, it's going to be to the left 4, down 11. The vertex will be here, which is, again, where is HK going to be? And it's going to be up and down. It's going to be downwards instead of upwards because of the negative sign on A, or it's going to be vertically reflected. And it's going to be narrower because of the 3. And again, I can kind of tell exactly what this is going to look like by understanding those transformations really well. And of course, you could always just graph it in a calculator. That's a way you can check yourself. Very, very strongly recommend this. But again, that's the point. And this is a very, very powerful tool as a math teacher for me to just sort of look at something and know exactly what it's going to look like. Because the graph tells us a lot of things like, well, what's the domain? What's the range? Where's the min? Where's the max? Where is it increasing and decreasing? I can do all of that just by looking at it. And that's one of the huge tools for being able to do math in your head.